Welcome to section 5.4. Here we're going to talk about logarithms. Now, I'm pretty positive that you're all familiar with logarithms. It's a topic that's taught in intermediate algebra and is sometimes reinforced in trig, which is the prerequisite for this course. And so they are super important, though, as we move into calculus. There's some ways that we use logarithms to minimize our work. And so we want you to be familiar with them again. And so let's remind ourselves about what logarithms are. They're the inverse function of an exponential. So let me write an exponential function, but instead of using f of x, I'm going to use the letter y, right, for f of x, and say y is equal to a to the x. Remember, a had some conditions on it. A had to be greater than 0, and a could not be equal to 1. Well, if we have that exponential function, then the inverse function, and it goes either way, is the log function. And so the log function is log base a, the base is the thing that you're raising to a power, of y is equal to x. Right? So what are logs? Look what log is equal to in relationship to what's up here. Logs are exponents. So that's why in the next section, when we talk about the properties of logs and the ones that you already are familiar with, you know that they're just the exponential rules, that if you multiply two things, you add the exponents. If you divide two things, you subtract. Logs are exponents, if you keep that in your mind. So that should give you a vision of why they're so important. Sometimes the variable that we need to solve for is up in the exponent area, and the way to get that down efficiently is by applying a log. So let's talk about the domain of a log function. The domain of a log function is not everything. The domain of a log function, let me just write an in general log function. Let's look at f of x is equal to log base a to the x. Let me not confuse the x's and y's. That's what's allowing us to discover the inverse function. But if we look at the in general log base a of x, it's important that we always remember the domain. The domain is not all reals. So remember what log base a is not log base a times x, it's log base a of x. So if there's nothing there, it doesn't make any sense. But we're basically asking ourselves, what power do we raise a to in order to get x? Well, because a is positive but not 1, the domain is not even from 0. You can't even obtain 0. Think about the exponential. Remember where this is coming from. It's coming from the results of the exponential. In the exponential, why we had you graph it, looks like this. Look at what its range is. It doesn't ever get to 0, so it doesn't include 0, but goes as high as we want. Remember, it's the y values of the exponential. And the range would be the domain of this function, or negative infinity to infinity. You can get any power out, but you'll never get something of taking a positive number to a power that's going to be 0 or negative, and so that's why the domain's that way. So for example, let's just look at some evaluation of logs, make sure we understand them. What's log base 3 of 27 equal to? Well, we just have to ask ourselves, what power do we raise 3 to in order to get 27? That's what this question is asking for. What power is 3 raised to get 27? I'll keep those two twos together. I don't like it, but I'm not going to change it. To get 27. And so that's the question, and hopefully you know that that answer is 3. Now, if you didn't know that is the answer, you could always say, okay, I'm looking for 3 to the x is equal to 27. You could always translate it out to its exponential. And so they'll do some work with translation, but I just wanted to make sure that you understood it. So log base 2 of 16 is equal to 4. Why? Because 2 to the 4th power is 16. Remember, this is the exponent that's on the base. Now, I may be going too basic for you so you can fast forward to this, but if not, then that's why I'm talking about it. So we're just looking for that. I do want to remind you that if there's no base written, so if I do something like log of 1,000, that's going to be 3. Now, why is that 3? If there's no base written, that translates to our base number system of a 10. So because we do things in base 10, and that's the most common thing, we just leave it out. So if it's ever left out, there's no missing base there. The base is 10. Just like when you see this, you know the answer is 8. Now because we use the square root most often, we don't write the 2 there, but there's an implied 2 there. Any other root that I'm going to have to show, so it's along the same lines. They're looking at that in that way. The other thing that comes up a lot, because we deal with practical problems that occur in real life and in nature, is E. So if you ever see ln of some number, well, that's going to be an E. So I just wanted to make up a true statement there. So ln of 1 is the same thing as log base E of 1. What power do I have to raise e to in order to get 1? Do you understand why it's 0? Anything raised to the 0 power is 1. We saw that as we did the graphs in the last section. It wouldn't matter if that's a 3 or a 5 to the x. Anything to the 0 power is 1. And so that's what the log is looking for. Hey, what power do I need to raise e to in order to get 1? So no base written, 10, if it's a log with no base. If it's an ln, it's base e. So they'll have you do things like translate logs into exponentials. So if I do something like log base 5 of 125 is equal to 3, the homework might ask you to translate into the exponential. Easy. 5, the base, to the exponent, 3 is equal to 125. So if we had log base, log of 100 is equal to 2. They want you to say, oh, that means 10 squared is equal to 100. They'll always make a true statement there. They might have something like this eventually. Log base x of 36 is equal to 2. And then you would write, oh, okay, that means x squared is equal to 36, and then solve that. Okay, what's x going to be? Right now I'm just translating out, but later on we would solve that logarithmic equation. It illustrates that a lot of log equations, so if I do something like log base 2 of x is equal to 5, well, it's easy to solve that log equation. Just translate it to its exponential and solve. Both of those are going to be quickly solved by you. This one is from arithmetic, and this one is from pre-algebra, reinforced in your algebra classes as well. Awesome, right? So it could be something like that. And we could also have this log base 3 of 81 is equal to x. And you'd have 3 to the x is equal to 81 as the translation of that. Okay, so that's translating logs into exponentials. We'll have us change exponentials into logs. Maybe they'll say something like e to the second is equal to, I don't know what e to the second is. I will find out though. Okay. Is equal to 7.389. And so you translate that into its log statement by putting ln. ln is better than log base e because it's a button on your calculator that you will recognize. Now remember, it's log of the answer is equal to the exponent, right? So if we had something like 9 squared is equal to 81, no problem. That's a log. Base is 9 of 81 is always equal to the exponent. And so they're stressing that exponent type of work right there. And so that's going to be a little bit of your work there in the 5.4 section, but welcome one. So it's like every time we deal with logs, they make sure we translate it. So they're going to have us look at some log functions. So the third problem I want you to take a look at is something like this. Find the exact value of And I'm going to stop for a minute. Whatever they put after this is going to be easily solved if you understand logs. So it's going to possibly look complicated, but if you understand logs and powers and things that were taught to us previously, it will not be complicated. So here's a problem that I saw in the homework. Log base 4 of the fifth root of 4. Now what makes this a nice problem, and I'll highlight it, is that these 4's are related. So remember what log's asking. What is this problem asking? It is essentially asking this question: what power do I need to put on 4 to get the fifth root of 4? Well, think about the fifth root of 4 as a power. I think you know about rational roots. I hope you do. It was a big concept in intermediate algebra that we use a lot in the future. This is just 4 to the 1/5 power. Do you remember that? So take a look at it. It's very visual. Remember the question: what power do you have to put on 4 to get the fifth root of 4? What power do you have to put on 4 to get 4 to the 1/5 power? Of course it's 1/5. Again, it's going to be pretty simple if you're looking at that. Now, the next question that I saw in the homework, next style, is asking about domain. What is the domain of f of x is equal to 7 minus 2 log base 3 of x over 2 minus 9? Okay. Here's what you need to know. Doesn't matter. The problem that we're going to have is not being able to subtract the number away from 7. Never an issue. The problem that we're going to have is not doubling a number. Never an issue. The problem that we're going to have is what the log is operating on. It doesn't even matter what the base is. The 3 doesn't matter. All that matters is that whatever the log is operating on, I'm going to scroll back up here. Hopefully that doesn't make you dizzy or anything. Remember, the domain of any log function, regardless of the base, is whatever the log is operating on must be positive. It cannot be 0 or negative. So what do we care about? We care only about x over 2 minus 9 being greater than 0. Or x over 2 being greater than 9, or x being greater than 18. What's the domain? That's it right there. 18 to infinity is the domain. It's that easy if you remember that you can't take the log of anything. There is no way that you're going to take 3 to a power and ever get a negative. You're like, yeah, you will if I put a negative exponent on. Then you don't understand what negative exponents are. Because if you don't know, if you think 3 to the negative 1's negative, you got big issues moving forward. Because hopefully you know by now that a negative exponent just turns you upside down. Right? A negative exponent is the flip. They've been teaching that since pre-algebra. We need that knowledge now. Right? So you're never going to get a negative number out of taking 3 to a power. We graphed already 3 to the x or something like it, and notice it never goes negative. That's why we want the graphs in there, so you don't have to just be like, I don't understand. You can visually see in that. So they're going to give us, continue with this vein, and the fifth example that I want to look at is something that happens towards the end. They give you a log function, and they ask for its domain. They ask for a few things. They want to know the domain of this guy. No problem. The domain of this guy is when x plus 1 is greater than 0. So the domain is negative 1 to infinity. They ask us to graph it. No problem. We'll get the graph in there. And so if we go to get the graph, how do we get that graph? We just start thinking about things. Okay, so we know our domain's negative 1 to infinity. Okay, it means we can't plug in negative 1. So let me go where negative 1 is, and I'm going to put a red vertical asymptote because we will not be able to cross that. Okay. So as we put in something, as we think about what the log function might look like, well, let's plug in something like, like 0. Okay, so this plus 5 is going to do something to us. The log, the x plus 1, so it's going to take a regular log function, shift it left 1 and up 5. Let's investigate what a regular log function would do. If we just looked at something simple like f of x is equal to log x, that might be the best way to talk about this. What we know is that we can't plug in 0. So I'm going to come in here, I'm going to get rid of those crossbars and do them in black. And because I'm going to come in here and put in red this guy right here. We cannot cross that line. So notice that that vertical asymptote has moved back 1 unit, which is exactly what we expected based upon our shifting. We know that if we plug in 1, log of 1 is 0. And actually, let me put a base in that. Let me put log base 2, just so we have a number in there. I know we had a number with 10, but I wanted it to be smaller than 10. So let's think about this. If I chose 2, I'd be up a height of 1. If I chose 4, I'd be up a height of 2. And I'm going to look just like this, and you know what happens around a vertical asymptote. We go down to infinity. So I get this growing graph that looks like this. Okay, so what's going to happen? This unit right here is going to move 5 up. So what I do know is that it's 1 over from my center, and it's going to move 5 up. 1, 2, 3, 4, 5. I'm going to go right there. So notice if I plug in 0, I get log of 1, which is 0, and I'm going to move up 5. And then we know what's going to happen from there. Going to go up like that and down like this. So we get a nice quick graph of that. They're going to ask us for a range, but we already knew what our range was going to be. Negative infinity to infinity, right? It's not going to change. We're just shifting things left, right, up, and down, but it's still going to span the entire graph. Does it have any vertical asymptotes? Of course it does. It's at x equals negative 1 that we have a vertical asymptote. And so they're going to try to fold in all that language. And so the interesting thing that they're going to ask us to do is they're going to ask us to find f inverse of x. So let me remind you what f of x was. So I'll put a question mark here. F of x was log of x plus 1 plus 5. So this is the fun part. This is the algebra part. This is the calculus part, right? The hard part about calculus is the algebra cleanup. But they're asking for f inverse of x. Not easily just quickly jotted down when you have a complicated log like this, but easily figured out if you just follow the process. So remember what the process would be to find f inverse of x. It would be interchanging the x's and y's. So I'm going to come down here and do it in blue. So if we're going to find f inverse of x, I'm going to do it more here to the middle. I'm going to take this f of x, I'm going to make it x, because it was a y, equals log of y plus 1 plus 5. A new function. That's why I'm putting it in blue. That is the f inverse function. Now I don't know it until I solve for y, just like every other time you've found inverse functions, including in this class. And so now we're just patient. So you know what we need to do. We need to isolate the log. Now here's where we apply the fact that a log is the opposite of an exponential. But better stated, here's what you're going to do. You're just going to write this log statement in its exponential form. So what's the base? The base is 10. What's the power? The power is x minus 5. What's it equal to? Y plus 1. 10, right? The 10 that's right here to the exponent is equal to what log's operating on. No different than the basic problems that we did back here, right? When we had these guys, we said 3 to the x was 81. When we had this one, we said x squared was 36. When we had this one, we said 5 to the third is 125. No different. That's the best way to unlock a log, is to write it in its exponential form. So 10, right? There's an unwritten 10 right there. Let me erase that so it doesn't cause confusion. 10 to the x minus 5 is equal to y plus 1. And then there's one last thing to do. Well, there's two things to do. The last thing to do is relate this back to f. But there was only one thing to move over. Awesome. F inverse of x is 10 to the x minus 5 minus 1. So I wanted you to have some examples of that. Very, very good algebra involved there. Very good applications of applying the definition of logs, right? To change it to its exponential statement, which is how we solve log equations, as you probably remember from both intermediate algebra and any reinforcement of logs later on. So let's look at solving a log equation. I saw this one in the homework. If you're going to solve a log equation like this, your first go-to should be, can I write it in its exponential form and be able to solve it? Let's try it. The base, 2, raised to the exponent, always what log's equal to, is equal to what log's operating on. We can solve that. 2 to the 4th is 16. Minus 3 minus 3, 13 is equal to 4x. Divide by 4, divide by 4, x is equal to 13 fourths. Now, before you call that the answer, remember, the log's domain is not all reals. So you must respect the fact that the answer that you got may not be able to be used, and there's no solution. So if I check the 13 fourths, all I care about is whether log base 2 of this number will equal a number. Well, I care mainly about, let me restate that, is this 4x plus 3 going to be greater than 0? And it is. If you plug in 13 fourths, you get 13 plus 3, which is 16. No problem. I mean, if you continued to check that, you'd realize, oh yeah, that's perfect. Log base 2 of 16 is 4, right? And we're doing good work along the way. This is perfect. And then the last question that I want to model is the same. I just want to make sure that you're understanding what we can do. Now they're keeping this relatively small, but we're going to look at this as, hey, let's try 2 to the second power is equal to x squared plus 3. All we did was the basic translation from log to exponentials. 4 is equal to x squared plus 3. Okay. And so we're going to subtract over the 3 and get x squared is equal to 1 and get x is equal to, and be careful here, plus or minus 1, right? Two answers come out of that. Now we got to check them. Do they both work? And now, are they both, maybe not say they both work, are they both going to respect the domain? And the answer is yes. Regardless of a 1 or a negative 1, squared would be 1 plus 3 would be 4. And we are finished. Now, what would happen if I did something like this? I'm going to take that 7, I'm going to change it just a little bit, and we'll do a side-by-side comparison. Let's suppose the question on the test looked like this. Same style of problem, but a little bit different. Do you see the difference? I'll highlight it. It's that x right there. Now you would have 2 to the second is equal to x squared plus 3x. Now you'd have 4 is equal to x squared plus 3x. Now you would bring over the 4 because it's a quadratic, and we've known that that's what we needed to do from our beginning algebra days, possibly pre-algebra, depending upon your teacher. Factors of 4 that subtract to be 3. Oh, those exist. 4 and a minus 1 would do that in respect to the positive nature of the 3. That means I have two solutions, negative 4 and 1. Now, do they both work? Well, how about the 1? 1 squared is 1 plus 3. Yep, that works. How about negative 4? Negative 4 squared is 16 minus 12, positive. Okay, they're both keepers. You'll find sometimes only one of them's a keeper, and sometimes you have to throw both out. But you always should be checking the domain. Anytime you have a function that has a limited domain and you're solving an equation, you should check to make sure that you're still in the domain, that your answers are even allowable. So some good tied-in types of examples to the homework. So try that, and hopefully all goes well in 5.4. But if not, reach out to me either through support hours or through email.